Modern computers at their core are electrical circuits. A very simple circuit might consist of a battery connected to a switch, then a light bulb, then back to the negative terminal of the battery. Modern computer components typically supply a voltage of 3.3 or 5 volts between the positive terminal and the ground, or negative terminal if you like to think of it that way. Computers treat information as binary, on or off, true or false, 1 or 0, based on if the voltage is high or low. The important component in our circuit here is the push switch, which comes in two flavors. Push to make, that's when a person presses down and the circuit is completed between the two terminals and the bulb lights up. The push to break switch is exactly the opposite. This is the symbol for a transistor. More specifically, it's a metal oxide semiconductor field effect transistor, or MOSFET. Its source and drain are like the two terminals of a switch, but it has a third terminal called a gate. Just like switches, there are two types. The N-channel type makes a circuit when a high voltage is applied to the gate, like a push to make. The P-channel breaks the circuit when a high voltage is applied, like a push to break. So transistors act like switches, except instead of a person pressing it down, a voltage is applied. In modern computers, these types of transistors are used in pairs, referred to as CMOS, or complementary metal oxide semiconductor. The gate terminals of a given pair are always connected together, so they receive the same input. Here is a simple example. If we apply a high voltage, or 1, to the input, the N-channel MOSFET opens a route between high voltage and the output. The P-channel closes the route to ground. If we apply a low voltage or 0 at the input, the P-channel opens a path to ground. Okay, so this circuit seems pointless. We got the same thing at the output as we did at the input. But let's swap around the two MOSFETs. Now, when we apply a high voltage, or 1, to the input, the N-type opens a route to low voltage, or 0. When we apply a 0 to the input, we get a 1 at the output. Whatever we put in at the input, we get the opposite at the output. Later, we will come back to how this forms the basis of all modern processors. Understand that it is vast networks of CMOS pairs like these which allow computers to think. For now, let's see how transistor networks are made in basic terms. Silicon is a semiconductor with 4 valence electrons, which is doped or mixed with other elements. Gallium, for example, has 3 valence electrons, one less than silicon, hence more positive, or p-type. Meanwhile, an element like arsenic has 5 valence electrons, one more than silicon, therefore adding a negative charge, hence n-type. Trace amounts of these elements, typically 1 for every million silicon atoms or so, are implanted by chemical diffusion or by firing them out of a particle accelerator. Transistors are made by sandwiching a region of one of the dopants between 2 of the other. Let's look more closely at the N-channel configuration. This by itself does not conduct electricity, but when an electric field is applied to it, a conducting channel forms, hence the name field effect transistor. This can be thought of in simple terms as the electric field attracting electrons from the N-doped region, which has a surplus, to the P-doped region, which has a deficit. Near the semiconductor stack, we have a conducting electrical terminal. When it's at high voltage, an electric field forms and the transistor conducts. But, to stop a short circuit, we need to add an insulating layer between them. The contact is metal, the insulator is silicon oxide, and finally we have the doped semiconductor, hence the term MOSFET. For a computer, we need millions of interconnected CMOS pairs, and they must be small and close together so that electrical signals can travel between them quickly. Making a processor typically begins with a solid block of p-doped silicon called a die. Transistors are then created on top of the die by a process called lithography, writing on stone. There are 2 main techniques used in lithography. The first is deposition, chemically building up a layer of controlled, predetermined thickness across the entire die. This means that, for example, N-doped silicon can be coated all over the top of the p-doped die. Unwanted surface material is then removed by a second technique called etching. This is done by applying chemicals or hot plasma to the top of the die. Several steps are taken to ensure that the etching is targeted at specific areas, and therefore material is removed selectively. A chemical termed a photoresist is deposited onto the die. Light is shined through a mask, exposing predetermined areas of the photoresist. The exposed areas must be the same size or larger than the wavelength of light used. Hence, very short wavelength ultraviolet light is used for lithography. A special etching method is used to remove only regions of photoresist which were exposed and nothing else. This opens up gaps in the photoresist. And then another etching method is used, which targets everything except the unexposed photoresist. Finally, the remaining photoresist is etched away. As a result, material has been removed wherever there are any gaps in the mask. The two techniques of deposition and etching used in conjunction mean that the N-type dopants for all the transistors on the die can be added simultaneously. Next, the silicon oxide is deposited and etched, and finally metal is deposited and etched away to leave metal channels on top of the die. These metal features form not just the conducting terminals of the transistors, but also the tracks equivalent to wires in a circuit, which connect the transistors as required. Every time photoresist is deposited, exposed through a mask, gaps are made and a die is etched. Finally, the billions of transistors are assembled and connected together by this method. There may be 3 CMOS pairs with 3 different inputs, then going out to 4 different CMOS pairs somewhere else, and so on and so on. To summarize, computers handle information as ones and zeros, when voltage in an electrical circuit is either high or low. Transistors act as electronic switches, changing between these two states. The transistors always come in complementary pairs, so when one half of the pair opens, the other closes. Lithography is the process by which huge numbers of interconnected transistors are built up on a block of silicon. To understand why transistor networks are useful, we need to talk about a branch of mathematical logic called Boolean algebra. Rather than go into the full gory mathematical details, I will just illustrate the basic concepts with some not too serious examples. Let's say some friends are choosing a restaurant. Alice is happy when the restaurant serves burgers. Bob is happy when the restaurant does not serve burgers. We can think of evaluating restaurants in this case as something called a gate, an object which takes a binary input, true or false, 1 or 0, and returns a binary output. In this case, the input is whether the restaurant has burgers, and the output is if someone is happy with the restaurant. For Alice, the gate is simple. The output is the same as the input. In electronic terms, the circuit is just a connection. For Bob, the gate is what's unimaginatively called a NOT gate. This is the symbol typically used to denote it. In the previous section, we have seen how this CMOS pair acts as a NOT gate. Let's consider a more interesting example when the logic gates can have multiple inputs. Such gates have pretty straightforward names, as we'll see. Now the friends are choosing restaurants which might serve pizza, noodles, both, or neither. Alice is happy when the restaurant serves at least one of the two options, or both. This idea is represented by what is called an OR gate. This is the symbol. Bob wants choice, so he wants both pizza and noodles on the menu, hence the AND gate. Charlie likes it if the restaurant serves pizza or noodles, but not both. Let's say she thinks that they wouldn't do a good job if they weren't specialized enough. The corresponding gate is called exclusive OR, XOR for short. Each of these gates also has a complementary gate, basically the same gate with a NOT gate after it. For example, the NAND gate gives a 0 when all its inputs are 1 and gives a 1 otherwise. These complementary gates are denoted by the usual symbol with a circle at the output. For a computer, these and all other possible gates must be implemented through CMOS pairs. Connecting two pairs as follows creates a NAND gate. The N-channel and P-channel transistors still work in pairs. Only when a high voltage, or 1, is applied to both pairs of inputs do the paths to high voltage close and the path to ground opens, so a 0 is output. This is exactly the behavior of a NAND gate. The NAND gate is important because it's what's called universal. This means that any other gate can be created out of NAND gates as long as there are enough of them. Now, there are more efficient ways to make certain gates, but in essence this means that the problem of implementing logic gates through CMOS pairs is solved.
There are also gates with 3, 4, or as many inputs as necessary. For example, take two AND gates connected as shown here, and they simply become a 3-input AND gate, and so on and so forth. To summarize, logic gates are conceptual mathematical objects which allow us to make deductions based on binary true or false statements. For example, if it's true that today is Saturday or today is Sunday, then it's also true that today is the weekend. We have now seen how the CMOS pairs from the last section can be used to practically implement these gates in terms of electronic binary logic.